Okay, this is section 4.2 on page 168 of your textbook. This is it's a short lesson, but it's a very, very important lesson. It's the introduction, basically, to all of grade 11, or a huge chunk of grade 11, and for the purpose of this course as well, so kind of the later half of this course. And it's called quadratics, all right? So the title is Quadratic Relations. So there's a lot of definitions that you're going to learn today that are going to be brand new, but will stay with you all the way through advanced functions in grade 12. Okay, so a short lesson, but nonetheless very important. Okay, and I don't know if you guys have seen any of this before. I don't think you have. But this is not something that is going to go away anytime soon. It's going to be with you, like I said, for the next 2 to 3 years. Okay, if you go into engineering, this is something that doesn't go away if you go into advanced mathematics at university. So, quadratic relation. What it is, it's a relation whose equation is in the form ax squared plus bx plus c. So, I don't want to confuse you too much by these letters in front of the variable x. But that's how we dictate them. That's how we separate them. The coefficient of x squared we label as a. The coefficient of x is b. And the last coefficient, or the last constant, is c. So a way that this would look written out would be something like this. Okay? So although this looks maybe a little bit strange, this should look a little more manageable in the sense that at least there's only one variable right here. Okay? There's just x, and then there's x raised to a higher exponent of 2. Okay, so in this case, who can tell me what the value in this equation is? What is the value of a? Gennaro? 2. 2, very good. Excellent, I thought I heard you say that. Good. Yeah, so the coefficient here, a, is 2. Okay, the value of b then, likewise, would be 3. And the value of c would be -7. Okay, if your equation looked like this, if there was a negative sign here, or even a negative sign in front of a, your values of a then become -2, b is -3, and c is -7. Okay? So I want you first and foremost to be aware of what this equation means. Okay, then to further define it, where we say a, b, and c are real numbers, so real numbers, that's the only numbers we know right now, are real numbers, so basically any number, and a is not equal to 0. So what that means is, if this case, if a was 0, then this equation, if that was 0, 2 was 0, then this equation would just be -3x minus 7. Right? So a has to have a value. So in other words, the coefficient of x squared has to have a value. Otherwise, y equals -3x minus 7. Can anyone tell me what that graph would look like? Or just what kind of graph it would be? Yeah, right? Linear? Yeah, it would be a linear straight line. Good, and that's what we're moving away from, as we learned in 4.1. We're going with nonlinear relations. So in that case, we know what we're saying, quadratic relations, a has to have a value. So this is the most important in the sense that there needs to be a value of a. There needs to be an x squared variable. Okay, that's what makes the relationship quadratic. It's this x squared. If you don't see an x squared, then you have, in all likelihood, a linear equation. Okay, there's another way we can tell that it's a quadratic, though, and we're going to talk about that a little bit. First of all, we're going to talk about a parabola. Does anyone know what a parabola is? What it looks like? Just a few of you? Just 4 of you? That's it? Dom, what's a parabola?
It's the graph. Is it a U-shaped graph?
Good, it's a U-shaped graph. Okay, the definition's there. Good, glad. Looks like that, yeah, just like a U. Okay, so what a parabola is, the definition is a graph of a quadratic relation. It's U-shaped and symmetrical. Symmetrical means that one side is identical to the other side. Okay, so just like on a linear relationship, a line is the description we would give the graph, or the shape of the graph. We would say that's a straight line. In this particular case, we would say in a quadratic, the shape of the graph, we would call it a parabola. Matthew?
Does the
always symmetrical through the y-axis?
No, no. Good question though. You can definitely have a parabola that's off-center not only from the y but also from the x. So you can have a graph that looks like that. Okay, so it doesn't have to be symmetrical through y. You can have another symmetrical axis of symmetry is what we call it. The next point we want to talk about is the vertex. It's the point on a parabola where the curve changes direction. And the example is a max or minimum point. So depending whether the curve is opening up or down, so there's an example of it opening down or up, your vertex is going to be either the lowest point or the highest point. It's also the point where the parabola changes direction. Okay? And all of the quadratics that we're going to be covering, all of the parabolas are going to either open straight up or straight down. We won't be looking at parabolas that open on angles like this. Okay? You won't even look at those in grade 11. You'll only start looking at those in grade 12 in advanced functions. So for now, all of your vertexes will either be a maximum point or a minimum point. Okay? You won't see anything like this where we have a parabola on an angle. Okay? So any questions about that so far? Max, min? That's called your vertex point. So it's a special point. It's an exact point. It has an x and y value. X and y. And it's special because it tells us a lot of the times a data point that we're looking for. So for instance, in advanced accounting, they'll make formulas like this and they'll have a graph. And you'll want to know when are the max profits. At what x value, or what independent value, do I have max profits? So what they're asking for is what is this vertex value? Right? What is the max profits? How many employees do I have to hire in order to get that amount of profits? Okay? Because as you imagine, if you hire a certain amount of employees, you hire more, you make more money, but after a certain point, if you hire too many, you start losing money because you got to pay those employees. Right? So you get this sort of this realistic parabola type graph in terms of your earnings versus the number of employees you hire. Finally, the axis of symmetry, it's the line that divides a figure into two congruent parts. So in other words of saying that, it's the line that runs right through the middle, including the vertex of the parabola. Okay, so this here is your axis of symmetry. Okay, and it's always going to be an x value. Does that make sense? Because a vertical line, as we know, is always like an x value. X equals 4, let's say. 1, 2, 3, 4. So that x equals 4 line, that's my axis of symmetry. Does that make sense? This up and down vertical line, that's your x value. Okay, that's your axis of symmetry. Okay, and finally, finite differences. It's differences of y values with evenly spaced x values. So very important here, we're checking the difference between consecutive y values, differences of consecutive. So in this case, you would write first differences here. All right, so this is very important. This is how we can algebraically identify whether a graph is linear or whether the graph is quadratic. So you guys should know by just looking at this equation here that the graph is, David, what?
Linear.
Good, it's linear because it's of the form y equals mx plus b, right? But a way that we can check that is if we check the first differences of consecutive y values. Again, making sure that the x values are separated evenly. In this case, -2 to 1, -1 is 0, 0 to 1, 1 to 2. We all have a difference of 1. So this is evenly spaced x values. Now we're checking the differences of the y values. So some people get confused here. You always make sure you subtract the second y value from the first y value. Okay, so we're going -7 minus -9. So -7 minus -9 is -7 plus 9, so that's +2. Then we do -5 minus -7, negative 5 minus 7 is positive 2 again. Bless you. And negative 3 minus 5 is positive 2 again. And negative 1 minus 3 is positive 2 again. So what we notice then is our first differences are all the same, which is 2. If your first differences are the same, your graph is linear. Okay, even though we haven't graphed it, we know that it's going to be a straight line based on this first differences. So algebraically, it's a way of telling you this is a straight line. Any questions there? So obviously then we wouldn't check the second part of this is second differences. We wouldn't do second differences because of course they're going to be 0. Right? Because 2 minus 2, 2 minus 2, of course they're going to be 0. So we wouldn't bother checking those. If the first differences are the same, graph is linear. So that's this point here. No, these are all in regards to quadratic, so I'll get to the quadratic in a second. Here's the graph of the quadratic. So the simplest quadratic, what's the a value here, Mark?
1.
Good, it's 1. You don't see it, but there is a 1 there. Okay? So the a value is 1. This is the simplest quadratic we can actually graph. What's the b value here, David?
X?
No.
No, nothing.
Which is?
0.
Good. The b value is 0 and the c value?
0.
Good. It's also 0, so you don't need to write in there plus 0, plus 0. It's just y equals x squared. So in this case now we want to check the first differences. So when I draw this first differences part of the table, I draw the line between these two because it's this minus this. So I keep that center line between them in the middle of my new line. So like that. That's how you draw the lines. Okay, so you want to keep that center line in the middle of your new blank. So 1 minus 4 is equal to negative 3. 0 minus 1. 0 minus 1 is negative 1. 1 minus 0 is 1. 4 minus 1 is 3. So we don't have first differences are the same in this case. They're not the same. We have negative 3, negative 1, 1, and 3. So if that happens, you then need to check your second differences. So again, I'm going to draw the new blank in the middle between the other lines. So this line is in the middle. Okay, and I don't have a square there. So now I want the difference between negative 1 and negative 3. So negative 1 minus negative 3. So negative 1 plus 3 is positive 2. 1 minus minus 1. So 1 minus minus 1 is 1 plus 1 is positive 2. 3 minus 1 is positive 2. So again, my second differences now are all the same. This, therefore, is a quadratic equation. And if I were to graph it out, it would look something like this down here. Okay, and remember, to graph these, you're plotting the x versus y values. You're not plotting x versus first or second differences. You're just plotting as you normally would. So negative 2, 4, I go negative 2, up 4. Negative 1, I go over 1, up 1. 0, 0, 1 and 1, and 2 and 4. That's how you plot it out. Okay, so there's a couple ways now that we've learned how to check for quadratic relations. One is ensuring that there is an x squared value in the formula. Another is checking the second differences, making sure they're all the same. And finally, taking a look at the graph and making sure it has the shape of a parabola. Okay, so our key points then, our relation defined by this equation is a quadratic relation. It has a graph in the shape of a parabola. The vertex of the parabola is either the minimum or the maximum point. So in this case, the vertex would be 0, 0. It's the very bottom point, the minimum point. And finally, a parabola is symmetric about the axis of symmetry. That's the line that divides the parabola into two equal congruent parts. And the last point, if a relationship is quadratic, the second differences are constant, but the first differences are not. Okay, so that's section 4.2. Mistake there. 4.2. Quadratic relations. All right? Any questions?